If an algorithm could crave instant gratification, then greedy algorithms would be the ones to. They want the best, and they want it now. Greedy algorithms solve problems step by step, and at each step make the best possible choice for that step. It doesn't care about the second order consequences of that choice, and once it's made a decision, it's not going to change its mind, so we don't retrace any of the steps. The point is that at each step, a greedy algorithm makes a locally optimal, or greedy, choice. It continues to make these greedy choices until a solution is reached, in the hopes that this amalgamation of locally optimal choices will lead to a globally optimal solution. Since we don't revisit steps, there is no repetition and the algorithm runs just once. This means that it's fast. It has an efficient time complexity, however, there is a possibility that we could miss better solutions. The solution we reach will usually be good, but may not be the best that it could possibly be. There are two main requirements a problem needs in order for a greedy algorithm to work on it. The first requirement is the greedy choice property. A problem has this property if the solution can be found by making locally optimal choices. The algorithm needs to be able to make the best choice right now without worrying about the second order consequences of this. Secondly, the problem needs to have optimal substructure. A problem has optimal substructure if an optimal solution to the problem contains optimal solutions to the subproblems. This means that after making a greedy choice, the subproblem that remains must also be one that can be solved optimally by applying the same greedy strategy. Greedy algorithms are often used for optimization problems, where we want to maximize or minimize a value at each step. In order to know what the locally optimal choice is, a rule is followed. We'll see what this means in a simple example. Let us take a look at this basic tree. We want to solve the problem of finding the largest sum of weights on a path down the tree, and we're going to use a greedy algorithm to do this. The greedy rule at each step is going to choose the node with the largest weight, so we're optimizing for a maximum value. At the root, 6 is the only choice we have, but on the next level, we have a choice between 2 and 7. Since our greedy rule states that we need to choose the node with the largest weight, we choose the node with the weight of 7, ignoring 2 and any nodes that come after it. Following 7, the locally optimal choice to make is 10, and so the solution to the problem that the greedy algorithm has found is 6 plus 7 plus 10, which is 23. If we see what other solutions there could have been, this would have been 13, 11, and 14. And so we can see that by choosing locally optimal solutions, our greedy algorithm has led us to the globally optimal one. However, as we mentioned earlier, it won't always do this, and whilst it will usually produce a good solution, it may not lead to the optimal one. Let's see what this would look like if we solved the same problem using a greedy algorithm using a slightly different tree. Here, we start at 6, and after that, the locally optimal choice between 7 and 2 is 7, and the locally optimal choice between 3 and 1 is 3. In this case, the greedy algorithm came up with a solution of 6 plus 7 plus 3, which is 16. If we look at what other solutions there are, these would be 13, 18, and 14. As we can see, there was a better solution, which our greedy algorithm missed. The solution it came up with certainly wasn't the worst. 16 is definitely better than 13 or 14 would have been. If we wanted to rigorously check every path, we could have used a brute force approach. And for a tree as small as this would have been an okay decision to make. However, in a tree much larger than this, brute force would simply be too slow, and so using a greedy algorithm, which has given us a pretty good solution in a much faster time, would have been the better decision to make. Greedy algorithms are often used for graph problems. Some of the most notable of these are Dijkstra's algorithm, Kruskal's algorithm, and Prim's algorithm. We're going to take a quick look at how Prim's algorithm uses a greedy algorithm design strategy. If you've never heard of Prim's algorithm, it's used to find the minimum spanning tree for a weighted, undirected graph. A minimum spanning tree is a subset of the edges of a connected, edge-weighted graph that connects all the vertices together with the minimum possible total edge weight. So, the greedy rule in Prim's is that at each step we look at all the nodes we've already visited and find the minimum edge weight that connects one of these nodes to an unvisited node, and then add that node and connected edge to the tree. This is optimizing for a minimum value at each step. We begin by picking our starting node. It makes no difference which you pick. We'll start at node D. Following the greedy rule, we choose the smallest weighted edge that connects D to an unvisited node. In this case, this is the edge between D and E, so we add this edge and node to the tree. Now we have two visited edges, D and E, so we pick the smallest weighted edge connected to either of these to add to the tree. This is the edge with a weight of 1, connecting E and G, so we add this edge and the node G to the tree. This procedure is greedy because at each step we are choosing to add to the tree the minimum weighted edge between a visited and unvisited node, and so are locally optimizing for a minimum. We don't care about future steps, only the minimum weight that we can possibly add to the tree for this particular step. And we also don't care about edges that are already part of the tree. Continuing on, the next locally optimal move that we can make would be to add node A to the tree through its connection to G. After this, we add F via A, B via F, and then C via F. At this point, there are no more unvisited nodes left to add to the tree, and so we have arrived at our solution, the minimum spanning tree for the graph, which is the global optimum. In our first example, we saw that depending on the structure of the tree, it was possible to follow a greedy algorithm and end up with a non-optimal solution. Prim's algorithm isn't like this, which is why it's such an effective greedy algorithm. No matter what, it will always lead to an optimal solution. To summarise, greedy algorithms solve problems step by step and make a greedy choice at each step, which means finding the local optimum. It keeps making greedy choices until a solution is reached. Greedy algorithms can be used for problems which have a greedy choice property and optimal substructure. Do let me know if you have any questions about greedy algorithms in the comments, because I'll be answering them all. Subscribe if you don't want to miss all the exciting content I've got coming out. Thanks for watching, and I'll see you in the next one.